Good day to everyone who's watching. This is the video for our application for the Sentience Grants program. Today we'll be presenting our research proposal, and the topic or the research area that we are focusing on is building a verifiable AI agents protocol. So I'll be starting out the pitch with basically showing a prototype, then going forward and showing which research directions we want to go in. Firstly, the first slide. What's the problem statement? So the trust gap in autonomous AI agent systems is widening. So autonomous AI agent systems are powering everything from financial trading to supply chain management, and soon will be powering most of the things on chain. But as they make critical decisions off chain, a growing trust gap has get emerged. Users simply have no way to verify what the AI agent sees, how it is deciding what to do, and who it really is. Let's imagine an AI trading bot for DeFi that suddenly goes rogue. It siphons funds and it executes unauthorized trades. Without cryptographic attestations, there's no audit trail, there's no accountability, and there's no way to distinguish between a malicious actor and a legitimate action. So that's what we're trying to combat here. This is the flowchart for our working prototype. We wanted to start out by building a version 0, which would account for some of the basic and fundamental necessities of verification and auditability for an AI agent. This is the flowchart, and we are basically basing it on three pillars. The first one being identity management for AI agents, second one being the input hashing and the input verification for AI agents, and the third one being execution logging. Like whatever the AI agent does, it logs the execution trail, and then it is then converted into a Merkle tree. That's what we're trying to do, and I will go in detail and talk about what our prototype achieves. Let's see what we're trying to do. First, there's a GitHub agent initialization. We have built a custom agent on the Sentient AI agent framework, which fetches README files from the given GitHub URLs and makes the summary. So this we have taken just as an example. Next, what we do is we do the cryptographic agent identity. We generate a did key pair for the agent and securely store it. Then we do the foundational on-chain attestation. So the wallet that wants to be associated with the corresponding AI agent is anchored to the AI agent's DID on-chain via a claim, and then we can bind this AI agent identity to the smart contract, Ethereum smart contract. Then what we try to do is we try to do the input root computation. So what is input root computation? We basically take the README files from all these GitHub repositories, hash them, and then what we do is we produce a single input root digest, and then we wrap the input root in a W3C compliant verifiable credential. We are using the library didkit and the didkit CLI for doing this, and we sign it with the AI agent's did key. Then when we have generated this input root, we want to also anchor it on chain. We publish the same input root hash under the KCAC 256 hash of the agent did key in the identity registry smart contract that we have already deployed on chain. This part concludes the AI agent input hashing as well as the identity management. Then we go forward and do the execution level logging. What we do here is that every step that the AI agent takes, for example, the tool calls, LLM inputs, outputs, are timestamped and hashed log entries. Then using these timestamped logs, we built a Merkle tree. When we are building the Merkle tree, we compute a single execution route after hashing all these leaves, and then we publish this single execution route onto IPFS, and we yield an immutable CID for it. Then what we do is package the execution route in the same verifiable credential, and we use didkit to sign it, and we then use the identity registry contract to anchor it on chain with the AI agent did key. So that's what we're doing. Also, we use zero knowledge verification. Basically, we have built a simple circuit for doing the Merkle tree construction, and then we submit the proof on chain that the AI agent has actually constructed the Merkle tree properly. First thing, as I told you, that we have built out the GitHub AI agent, which summarizes GitHub repos. So for that, what we do is when we put out this command and we put out some URLs, here we have taken the Go Ethereum repository as an example. What the AI agent does is make a summary for it. So this is the basic implementation, is the identity part. We generate a decentralized identifier for our agent and securely store its private key in the .jwk file. Then we run a file called publish foundational.py, which issues the foundational on-chain attestation binding the DID to our AI agent's registry. That gives us a cryptographic anchor. Anyone can look up the AI agents did on chain and verify it's under our control. That's what we have seen. So we are seeing here that we have uh, verified the on chain foundation attestation. Part is input hashing and verifiable credential. So before even the AI agents process anything, we hash the raw inputs. Here the readme text into an input loop. We then wrap it into a verifiable credential using the did kit. This credential proves that I used exactly these inputs without revealing the data on chain. Verifying it locally shows a clean proof check with no errors. This is the input route that we have generated. Is the execution logging. As you can see, this is the execution tree that you have collected. The AI agent runs, every prompt and call and LLM response chunk is timestamped, hashed, and appended into the leaf in the execution underscore tree.json, which is on the screen. Our framework's response handler emits these JSON events, so you capture a full ordered audit trail of the off-chain computation. And this is the verifiable credential file. Is the ZK proof generation. We have created a simple Merkle tree circuit which shows that the proof, which generates a proof for showing that the Merkle tree was constructed appropriately off-chain, and then we verify that on-chain as well. This prototype is just an example showcase to show our end-to-end verifiable framework. We have much more broader applications for this in DeFi, in automated trading systems, in insurance claim processing, in portfolio management. We also have extreme use cases in DAO governance, in automated smart contract execution. We also have use cases in supply chain management. So the use cases are unlimited, and you can use this framework to basically generate a verifiable AI agent. Now we saw the initial prototype that we had built, but then we are proposing even more. We want to dive in deep, we want to do more research. This was just an initial prototype by our team, but then we want to even explore ZKML, we want to explore T integrations, and we also want to explore policy constraints. So we have divided the research directions into 5 phases, and we have allocated time for each phase. First phase that we are going to try to do is policy constraints and benchmarking. Policy constraints are basically ZK enforced business and regulatory rules that the AI agent has to abide by. We are going to explore and research a way to auto-generate these policy constraints for every AI agent, and then we are going to use ZK VMs for benchmarking. This is what we are going to do research on. Next is critical point analysis. With the help of our mentor, we want to identify key verification points in AI agent computational flows and develop a method for determining high-risk verification nodes and create risk profiles for AI agent architecture. It's a very important phase of our research. Then we want to also use the Sentience TE enclave framework and create a hybrid model where we also use T attestations and ZK proofs. We want to also explore that in our research. Then we have a lot of experience in ZKML. In our previous research project, we worked with JP Morgan to design a complete ZKML framework for their automated trading systems. They had an ML algorithm which we had to completely make into a circuit using Circom, but that was a year ago. But now with the advancements in ZKML schemes, we can do much better, and we can also find ways where we can completely encode an LLM into a circuit. So we are also doing research onto this. For any more details, we have a complete document that I've compiled, that will be attaching to this email or the file that I've sent to you, where you can dive deep and see what exactly we're planning to do. Thanks a lot for hearing me out. And this is our team, which comprises of me, Akshat Gada, Rahul Roy, Krishna Doyapan, and our mentor, which is Pratosh AP sir, who is a professor at IASC Bangalore. Thanks a lot for hearing me out.